Good morning, everyone. Uh, Welcome to our today's seminar. It is my great pleasure to introduce our today's speaker, Professor Yang Huang. He is associate professor at the School of Astrophysics of the University of Chinese Academy of Science in Beijing. He did his PhD in 2016, University of Peking. And then he was for 2 years postdoc at LAMOST Observatory, also in the Peking University. His main research is focused on galactic archaeology from observational perspective, chemodynamical evolution, metal poor stars, elemental abundances, mainly in large spectroscopic surveys, big data. He's also an expert in machine learning techniques, and his other fields of research span almost the entire astrophysics. So I would challenge you to find any single area in which he's not actively researching right now. Apart of that, he's a really, really nice guy. I really recommend you, if you are interested in his talk, to reach him. He will be here with his student Hulin this week and next one in the context of the Chorus meeting. Chorus is the new spectrograph to be built for the GTC, and we will host Chinese community next week at ISC Tech. So for students, after the seminar, you could get your stamps with Alejandro. Don't forget about that. And I think there are some missing students. Okay, I'll note that. My friend, floor is yours. Thank you so much for being here today. And please go ahead.
Thank. So first of all, sorry, I just get a cold last day, and I hope my voice is fine. And okay, first of all, thank you for David's kind invitation and introduction. And it is great honor to be here to give this talk. And today I would like to share some progress on mapping the Milky Way with large-scale surveys, and the main focus on derived stellar parameters from photometric medium or narrowband surveys, and applying these parameters, particularly the metallicity, to uncover the assembly history of a galaxy. And I'm afraid I have no time to talk about dark matter. I will skip that. And here is the collaborators from China and also USA. Some of them are professors, some of them are students. And this is the outline of my talk, includes 3 parts. First, I will give a background introduction. So as I said, my research interesting focus on the Milky Way. So this galaxy is not only our own home galaxy, but also a very important benchmark galaxy to test galaxy formation and evolution. Simply because this is the galaxy, the only galaxy we can study in such a detail, to resolving individual stars with very precise 3D positions, 3D velocities, and some of them we can derive element abundance and even stellar ages. And if we have a large number of such stars with so many parameters, we can try to mapping its present structure and also try to understanding its assembly history. But this is not an easy task. So due to 2 challenges. For one, simply because we are inside it. I just put a Chinese poem here. So this is actually wrote by a very famous Chinese poet 1,000 years ago, when he climbed the very well-known Chinese mountain Lu, and I tried to translate it to English. He said, from the side, it's a bridge. From the front, a peak, near or far, high or low, the view is never the same. So we fail to see the mountain lose true face simply because we stand within the mountain. This poem just explained why we are hard to map the Milky Way's true face. Three things are very difficult. One is the hundred of billion stars span the entire sky, and the distance of each individual star are required if we want to get the true face. And very unluckily, we are in the mid-plane, and here we suffered very heavy reasoning, and it's hard to look toward the galactic center and even far side. But we astronomers never give up, try to paint a portrait of our galaxies. With the first effort from 200 years ago by William Herschel, although his picture is not correct. Nowadays, we briefly know that Milky Way is made by thin disk, and the surrounding is a stellar halo and a massive dark matter halo. And at the center is a bulge, and the very center is supermassive black hole. But still, there are many mysteries remained. For example, we don't even know how many spiral arms it has, 4 or 2, still under debate. And we don't even know the total mass of our galaxy precisely. Here is a review paper lists the past 10 years measurement of the Milky Way mass by different group and different people. You can see the values ranging from 0.5 times 10 to 12 to 2 times 10 to 12 solar mass. It's a big difference. And the second challenge is the Milky Way actually is a long-lived and long-involved systems. And we believe that the galaxy born just a few hundred million years after the Big Bang and evolved to today about 13.7 gigayear. And with the help of the simulations, we can see roughly how Milky Way-like galaxy grows up. You can see it is evolved quickly from at the beginning. You can see a prototype Milky Way, and then with lots of merges, some are major merges, some are lots of minor merges, and the star formation rate changes time by time, and the substructures are destroyed time by time, and also you can see the formation of the disk and bulge in the simulations. However, if we can overcome the challenging one, we can have a very good morphology of present day. But how to transport to recover these so many merges, minor merges, major merges, to look details how the star formation rate changes time by time, right? It is hard, and it is extremely changed to look the baby face of the Milky Way. We call it proto-Milky Way. What that looks like just after the Big Bang and the first star, first galaxy, our Milky Way, how it looks like. It is extremely hard, but still we have some tools. For example, we have the chemical. We have, if for metal poor star, can be indicator of age, can be, for example, minus 2.5. It can close to 11 or 13 gigayear. And also we have the velocity dispersion, that the old proto-Milky Way should be very hot. So the dispersion should be very large. And with these parameters, we can identify this remnant today. And with the help of the numerical simulation, we can try to recover how it looked like at the beginning. But this could only happen with a larger sky surveys, measures a lot of stars, and also precisely measures the velocity, position, and the metallicity. We can recover its signature. Very luckily, in the past decades, so the galactic large-scale surveys have improved significantly. From the very beginning, we have the Genova Copenhagen survey. At that time, it it surveyed the entire sky for nearby 100 for 10,000 stars within 100 parsec. And meanwhile, the Hipparcos mission also provide the parallax measurement for those stars. So this is the beginning of our large-scale survey of our galaxy. After that, you can see spectroscopically the target increased a lot. From SIGWI, the target from 10K increased to 1 million. And most recently, LAMOST have released 10 million stars with both low resolution spectra and also medium resolution spectra. And for astrometry and photometry, we now have Gaia. In the DR3, we have at least 1 billion star with very good quality data quality. And from the Gaia, it provides very good position, parallax, proper-motion, and mild-band photometry. From spectroscopic survey like LAMOST and also others, for example, ApoG, GLA, DAISY, and H3, it provides measurement of radial velocity, stellar parameters, including temperature, surface gravity, and iron metallicity. And also we can measure the element abundance ratio like carbon, alpha, and maybe mole. And combining this together, we can have a large sample with 460 phase space information. And some of them we have the chemical abundance ratios. And with help of the stellar evolution track, we can further determine the age. That is an indicator of the look back time. We can divide the sample of different age and to try to recover its history. And when I'm a PhD student, the first year, the LAMOST just start, and I'm very lucky to be a co-member of the LAMOST Galactic Anti-Center survey. This survey is want to have a very good sampling in the anti-center regions due to in these regions the reading is lower, and we can have a full sampling in the entire anti-center disk, and to understand the disk and the halo connections and disk formations. And you can see I'm also co-authors of the data pipeline and also the value-added catalog papers. And these surveys have achieved million stars. For some of them are dwarf within 3 kiloparsec, and some of them are joint stars. It can be as far as 10 kiloparsec. With this data, we have done a lot of things about the disk and also extended it to try to understand the connection between disk and halo. But if you look details, the number achieved by Gaia and the spectroscopic survey, you will find that the spectroscopic survey just measured 10 to 7, that is 10 million stars. This is significantly lag behind Gaia by 2 orders of magnitude. That means you will lose a lot of information about the galaxies, particularly because most of the surveys, the limiting magnitude are quite bright. For example, Gaia, LAMOST just limiting magnitude is 16.5, so it cannot touch very large volume. So is there any method to quickly fill the gaps? So this is the second part we have done in the past 3 years, try to derive more stellar parameter from the narrow or medium band surveys. So using photometric technique, the efficiency is much higher than spectroscopy, because for one over the field, you can, if you have good quality, you can derive using color or SED for information, you can derive all the parameters for the star down to a limiting magnitude. But for spectroscopic survey, you just select 10% or few percent. But you may ask how this photometric technique can be used to derive stellar parameters. What is performance? How it is compared to the spectroscopic surveys? So actually, we take advantages of 2 stellar atmosphere effect to derive the parameters using especially UV medium band surveys. For one is the so-called matter blackening effect. In short, more matter and more photons in the UV region could be absorbed and transferred to near-infrared regions. So here, I just plot several synthetic spectra with fixed temperature and surface gravity. And the color show different metallicity. For the black is solar metallicity. For the pink, it is -3. That means 1,000th solar metallicities. It's very matter poor. So you can see the matte blanketing effect. For solar metallicity, a lot of matter here absorbs a lot flex photons. And for the matter poor star, is almost is just absorb few photons here. So if you place filters here, for example, V, and combine V and G and plot here, and if we have another band R here, G minus R can be an indicator of temperature, and V minus G now it could be indicator of the metallicity. Here the data point is real data from SkyMapper. You can see that the sequence means different metallicity. From the red one, from very metal rich 0.5 dex down to -3.5 dex. The sensitivity is very good. You can see the sequence clearly. So that means if you measure a star with V minus G and G minus R, you can easily know its metallicity. And another effect is the Balmer jump effect. In short, the more luminous star, the more deeper jump. You can see here, we plot some other synthetic spectra with fixed temperature, now fixed metallicity, but different surface gravity. For this pink now is supergiant star. For this black is dwarf stars. You can see the supergiant star have the biggest jump, and the dwarf star have the least jump. If you have filter U and filter V here, U minus V could be used to an indicator of the jump, and then you plot in this diagram. Also, again, this is a real data point. You can separate dwarf star and giant star clearly. So using this method, we can using narrow or medium band, we can determine the metallicity and the surface gravity, and for temperature, the broadband color is okay. So most recently, several telescope projects installed such filters. For example, the SkyMapper and the SAGES, they both have U and V. One in south Siding Spring, and another it is a 2-meter bulk telescope out of the northern, and both. And the SkyMapper actually observed the entire southern sky. But for this disk region, due to the poor photometry quality, it's hard to extract the photometry correctly. So just a few of them have photometry. But other regions, the photometry is very good. So we can derive stellar parameters for over 50 million stars using SkyMapper. And for SAGES, also we achieved more than 26 million stars in the northern sky. And when you may ask how good is the metallicity estimate from the narrow band, here we show you cross-match result to the high resolution by David, and this is from medium resolution. This is again high resolution. You can see the results is very good. So when you calculate the scatter or dispersion, you can have a estimate of the uncertainty. For matter rich, it is about 0.1 dex, and the matter poor, mean matter poor is 0.1 to 0.2 dex, and the very matter poor star also have better than 0.3 dex. So this performance are close to the low resolution result. And for for Sam's project, they installed more filters. For J and S plus, they both have 7 narrow bands. You can see some of them are located in the custom HK lines, and some of them are located at the carbon G band, and some of them are located at the magnesium triplet, custom triplet. This means that you don't not only can determine the metallicity, but also can determine some of the element abundance ratio. For example, the carbon and the alpha abundance. Again, we compared to the high resolution result. The metallicity is it can be derived down to -4 or -3.5, and all the performance are even better than SkyMapper and SAGES. And also we can determine the carbon abundance. You can see the carbon rich, carbon poor can be recovered. But for alpha, we can do moderate uncertainties because magnets and the custom features not as strong, but still we can give a rough value. So in this manner, we totally derived 19 meaning stars using the 4 surveys. And most of them have stellar distance, and some of them have the radial velocity from spectroscopic survey, and some of them have the carbon and alpha abundance measured. Half of them have the stellar age measured. This is a big data for us to understand the Milky Way when combined to Gaia DR3. And most recently, in Gaia DR3, they not only provide the astrometric information, but also provide low resolution spectra for over 200 million stars across the sky, all sky, and the resolution is about 20 to 17 and covers the entire optical region. And the limiting magnitude is about 17.6 in G band. You can see here with some scanning strategy, scanning patterns still here, but it's a larger of numbers. And although the resolution is low, but each pixel or each wavelength pixel is well flex calibrate. So that means this can also be thought as another kind of narrow band. So when you plot the LCD information and at a fixed color, you can also see the blanketing effect significant from metal poor to metal rich. So we collaborate with Chinese AI Institute to develop an AI foundation model to handle such a large database. And we put all the spectra into this AI model, and we then can deliver atmospheric parameters and some of element abundance, including carbon, alpha, and nitrogen. And also because this have so many data points, we can also determine the reasoning. And I just show you how good it is. This is the reasoning map made by the spectral clip. You can see it's very beautiful. When compared to the IRA's far infrared image, most of the details are very close. You can see corresponding one by one. And also we can determine the metallicity for even down to metallicity -3. And here I show you, this is also very good tools for any student or any guys want to use these tools. So it is not only can derive stellar atmospheric parameters for Gaia XP, and also can be used to determine parameters for LAMOST-like spectra, or for example, LAMOST, SDSS, both spectra, and also the DAISY spectra. I show you examples by a video. You can see here. I just try to download one spectral from the LAMOST website. You can see I just found the target. You can see the official pipeline cannot derive the metallicity and log G temperature. It failed to generate the parameters. And then I download the spectra out. Just download the feed files to your laptop, and yeah, and then wait a minute, to upload to this website we designed. You can see we actually released the data here, you can see, but you can use these AI tools. You can just upload the downloaded spectra to upload. And will automatically analyze the spectra, and this continuum normalized spectra out, give you to show, and then just write what the information you want to say here. For example, radial velocity here. Yeah, we'll give you a result. And also he will give some related questions you want to ask. And you also can to ask him to give all the parameter out. Yeah, lots of parameters. It's also quite fast. All of them are here. And you can see now we are interested in the temperature, and metallicity is a -3 star. That's why the official pipeline cannot derive the metallicity, because the official pipeline can only derive metallicity down to -2.5, failed to derive metallicity for such a poor star. And sorry, sometimes we'll print Chinese out, but you can force them to print English. Yeah, in English. Yeah. And even you can ask how real such a star in the literature. Yeah. Or yeah, you can do a lot of things here. If you want to try, remember this website and have a try after this talk.
It's public, right?
Huh?
It is public.
Public. Yeah, public. And with the effort made by this narrowband survey and Gaia XP, now we increase the number of stellar parameters to maybe 200 million. So increase a lot. We filled some gap, but still 5 times lag behind Gaia. But we have a bright future because we have the JPass in Spain not actually operated this year. They have 50 narrowband, and in CSD we also have the slitless spectral graph similar to Gaia. Both of these telescopes can achieve the limiting magnitude down to 23 or 24. This is very deep, so you can catch a lot of stars in the sky, and we can detect over 1 billion stars achieved eventually after the mission of these two surveys. And at that time, Gaia DR3, DR4, DR5, we can match each other, and to give a global view of the Milky Way. At that time, we have the 460 element abundance measured for at least how to say 100% sampling, or 10. I forgot. Okay, this is a number. Yeah, and with narrowband surveys with such a large number of data, we now can actually do something, especially to trace back how the proto-Milky Way looks like using a large sample of mighty poor stars. So we try to see how it looks like at the beginning phase of the Milky Way, and the method. So here this diagram show you the mighty poor stars from the 4 surveys. So this actually is not just the mighty poor RGB sample candidates. Okay, this is mighty poor candidate, and for mighty poor stars poorer than -1, it is over 1 million. And for -2, between -2 and -3, it's about 300,000. And even below -3, have 20,000 stars here. So you can see the distribution is more close towards the galactic center. Actually, some papers claim this is a mighty poor heart. But we don't choose the very center due to the reasoning. And we now want to map the proto-Milky Way using these mad-poor stars. Before do that, we want to check that the most recent simulations suggest what the proto-Milky Way looks like. So, for example, according to the simulation results from this paper, this suggests that at the beginning phase, the gas is very rich. So different filament can be directly go to the potential, the deepest potential, actually the galactic center. So each filament touch each other, can take away the angular momentum that give you a weight compaction that can produce very compact bulge-like structures. So this theory can naturally explain why we observed some massive galaxies at redshift 2 are very compact and quiescent, and the effective radius just 1 kiloparsec. It is hard to explain by the angular momentum conservations. If like that way, the effective radius should be larger. But observations, we normally see such a dot-like galaxy, and in this series, they will predict the beginning. At the beginning, we have the so-called blue nugget phase. What is blue nugget? It is a compact gas-rich star-forming system. It is a progenitor of red nugget at observations. So this is the general picture. So you at the beginning, when the Milky Way is very small, you have a velocity dispersion supported system and have large star formations. And then when the Milky Way grows to 10 to 10 solar mass, and then you have the potential to protect the infilling gas, and then you have the central quenching, and then you have the red nugget. So how to quantitatively to measure such a blue nugget phase? So people do such a way to define the specified star formation rate. And you can see here at the very beginning, if you have a lot of gas infilling, then the specified star formation rate will go higher. Then you will have a lot of star formation rate. And then the gas is used, and then the star formation rate decreased. And then again, infilling gas. So a cycle, when all the gas is used, then quenching. So based on this picture, could we identify such an event in Milky Way-like simulations? So we tried similar ways to the Auriga simulations. One of these, this is Auriga 18. We picked it because this Milky Way-like galaxy is very close to Milky Way in mass and also in the formation history. For example, it also have the GES event, and also it's buried. So we try these simulations and to calculate the specified star formation rate along the stellar mass of the Milky Way. You can see at the very early phase have some bump like this. Maybe in this simulation, we experienced 3 starbursts, and then end up at this mass and then quenching. You can see roughly here. And when you plot the star generated by this phase, you can see this is the star at that time, not spherical, some shape at that time. But this picture is to involve all the stars to present day. You can see close to spherical system. And then we can compare these stars to our observations, these mad-poor stars, right? We can compare it by, for example, the spatial distribution. So here, this is we collect all the star, generate that phase for different metallicity beings for metallicity between -2 and -1, -3 and -2 below -3 can, when metallicity decrease, the shape is more compact at the early phase. And this is observation result. Although there are some selection function, but generally we can see a similar trend that more matter pool, more toward the galaxy center. This is 3D distribution. This is a 2D distributions. And also we can check the metallicity distribution functions along different radial beams. At the very center, you can see a peak here, a peak observed by the matter pool star. Maybe this is due to some starburst event at the very beginning. It is the peak point is -2.7, and here is it's turned to 3 to 6 kiloparsec, and this peak get weaker and weaker when you go too far away the center. And also you can check the kinematic. You can see here, this is the V5 along metallicity for both observation and the simulations. You can see a 10 point here, so-called spin up. You can, even though there are some offset, but the trend is almost same. So the real data turned on -1.5. And the observation, the simulations turned around -1.8. It's close, but in this phase, this is why spin up here is because you can see here again. This blue rocket phase end up this metallicity, and this metallicity end up this mass. This mass corresponding this value is a spin up point. So we tried for the first time to using numerical simulations AU18 as a Milky Way-like galaxy. And we propose a new scenario that the formation of the proto-Galaxy is linked to the epoch of high redshift gas compaction, the so-called blue gas phase, and then quenching give you the opportunity to the spin up. Okay, so finally, I want to summary to not to say again about what I talked. I just want to give some history view of our galaxies. So just 100 years ago, here this point. So Hubble determined the distance to M31 that end up. Before that, we astronomers believe that the universe is our galaxy, right? And just after that point, then astronomy believe actually the Milky Way is just one of normal galaxies. And Hubble established the observation cosmology. And then a lot of very, very important point happened in this branch. But our Milky Way become a normal galaxy. We struggle to self-paint our portrait. And with 100 years effort, we now have some rough picture, but still not enough, right? But now we are in a survey era. This is a golden era. So it is a very good chance to rediscover our galaxy, right? So that's all. Thanks.
Thank you. Thank you so much. Very nice talk. Inspiring. Thanks. Questions? Maybe I can break the ice. How do you deal with white dwarf contamination when deriving metallicity for your stars?
I actually made some so most of the blue white dwarf are cut because we have a color cut to exclude the star hotter than, for example, 7,000 Kelvin. And for some faint and cool white dwarf can be cut by the absolute magnitude. Yeah.
Okay.
Yeah.
How do you know the absolute magnitude?
Most of the stars have the parallax then.
Yeah.
Yeah.
Okay. I see.
Yeah.
So you can only close by white dwarfs to be removed.
Yeah. And another thing I forgot, I don't show here is because we have a library to give the label of the from spectroscopy. In the library, there are no white dwarf. And we have a quality flag to tell the star, compare the star to the library. If it looks like close like to the library stars and give you quality 1, if not, 0. So if a white dwarf slipped in the sample, you give a quality 0, you can exclude it easily.
Okay.
Yeah.
Thank you.
Yeah.
More questions? Desmond?
Thank you very much. Very nice talk. Actually, it's similar to your question. I think it's about binaries. And I mean, I know we're giant stars mostly, and a lot of them are supposed to have companions. Some are white dwarfs, but some are just other evolved stars. Do you see this when you do the spectroscopy? Do you have ways of mitigating it that you don't get?
Very good questions. So when you read the paper, we suggest first of all, you should exclude the star with RUI greater than 1 point, for example, 1.4 or 1.3. That can exclude significant binaries. And even with such a cut, you still some binaries can in the as a contaminations. So we now consider, for example, the spectral clip method. We want to put some binary inside and to training together with metallicity and binarity for the star with SED formations. Yeah, yeah.
Nice, thank you.
More questions? People on the Zoom? People here? Don't be shy.
Can you hear me? Yeah. So thank you for the talk. It was a very nice talk. But I should confess I was here for the dark matter. So can you say a few words about the dark matter? Do you think you can, with the Gaia data, say something about the clumpiness of dark matter in our galaxy?
Wait a minute. Okay. So I don't prepare I should prepare something. Wait a minute. Difficult here. For dark matter, the first thing we want to using so many data to measure the rotation curve of our galaxies. So rotation curve of our galaxies is extremely hard to measure. At the very beginning, we just have the H1 data to measure the rotation curve within the solar radius using so-called tangential method. And then with spectroscopic survey with radial velocity only, we can using some standard candles to measure with some assumptions and to measure the rotation curve. But now with Gaia, we can measure the real 3D velocity and to correct asymmetric drift and to give the very good rotation code. For example, here, this is a review paper by the so-called the Parliament 2000 this year, and this is a rotation code from Alice by Gaia DR2. This is ours from Gaia DR3. And this is for disk region. Now the uncertainties are small as few kilometers per second. And also we now try some very distant standard candles, for example, Alari star and BHB stars. We can extend the rotation code out to 100 kiloparsec. And the measured mass is about 1 times 10 to 12 solar mass. But still, this data is not enough because the very radius of our galaxy is about 200 kiloparsec. So still a lot of data, still of the matter are extrapolated by this curve. We just fitting out, but here we don't have data. We want to have data from, for example, JPass and CSD because the limiting magnitude can be very deep. And also in that way, we can determine the rotation code out to very reduced, maybe 200 kiloparsec and 250, something like that. Yeah.
But do you think you could see some inhomogeneities in our
Yeah. This is when we're using rotation code. Rotation code actually is a global measurement. And also our group doing to measure the local document density, which is very interesting for the particle test because they want to know the signal generated by the surrounding dark matter. So the density is very important. And recently we just using different populations, for example, thin disk and C disk, we find that the classical Jinsi equations cannot get a consistent result because our disk is dynamically young. The Snell's signature is sensitive to different populations. For hot, for cold, the signal is different. It's hard to remove such signals. So we recently followed some ideas by, for example, by the pulsar timing. With pulsar timing measurement, you can measure the acceleration directly. So there are some paper claimed that they can measure the local document density using the acceleration data. But the pulsar now just have maybe 10. This is not enough. So now we joined the, China now have the fast 500-meter radio telescope. It's very sensitive to observe a lot of pulsar. So we can, so also there is a group called the CPTA. They want to measure the gravitation wave from supermassive binary merge. And we can work together with him. They can measure such signal, but we can measure the acceleration of the pulsar at different locations. Yeah.
Thank you.
Yeah.
Time for a couple of more questions. Maybe people on Zoom. Okay. Thank you.
Thank you for the very nice talk and very nice introduction of the whole field. What is the age precision that you can derive at different ages?
The position.
Age precision.
Oh.
The precision in age.
Okay. So for 10 of stars and subgiant star, the position is about 20%. I can show you a plot. Yeah, this is the open, we calibrated the age determined by I-square fitting to, for example, here is open cluster, and this is open clusters. You can see the absolute magnitude is like this, and this is the absolute magnitude, 0.16 giga-year, and this is 0.07 dex, something like that for open cluster. For some field star, we can compare it to the spectroscopic sample, but for open cluster, we can examine how good the age you can see here. Yeah.
Very good.
Yeah.
Because it's photometric everything, right? So it's
yeah.
quite good. Yeah.
Yeah. Thank you.
Someone else? Well, I think we can wrap up here. Thanks the speaker again. Students, go to Alejandro and get your stamps if you want to become a PhD. Aha.